So far in learning our rules about integrals or integrating, we have only been able to integrate functions that use the opposite of what we call the power rule for derivatives. And so um, we were kind of limited. If it didn't work with the power rule, or if it wasn't the opposite of a trig derivative, then we just couldn't do it. And so there's got to be a way to undo functions that are chain rule functions, that are composite functions. And so that's what we're going to take a look at today. We're going to do anti-differentiation by substitution, which means that problems that were kind of like this before, like if I had of the function y equals, let's just say x plus 3 squared, if I had been taking the integral of that function, then I had to multiply it out, and then I could use the power rule. But with what we're going to learn today, there's a way to do this without having to multiply it out first. So remember that our chain rule for derivatives said that if we have a function inside of a function, we take the derivative. It's the derivative of the outside function, inside stays the same, times the derivative of the inside function. So it would make sense that if we wanted to integrate this, all of this would have to be present. Not just this portion, but the derivative of the inside as well. And so that's true, that in order to integrate, you've got to have this part along with the derivative of the inside. And if you do, then you can go back to the original function. But if that inside part is not there, then we're going to have to make some adjustments. So normally, when we have to make those adjustments for U-substitution, which is what it's called today, we're going to let the inside function, f of x, equal u. And so the derivative of the inside would be the derivative of u. And so this is the concept that we're going to use in order to take the derivative using substitution. All right, so on the back it has the steps for U-substitution. It says we want to choose our value for u. Today they're going to choose that for us. Then we're going to take the derivative of u and solve for du, and then make our substitution into the original problem, and then we'll integrate. So here's how this works. In this first equation here, they have chosen u to be the inside function, x to the third plus 5. So if I were to take the derivative of u with respect to x, I would get 3x squared. So this with respect to x is kind of important, because in order to use U-substitution, if we're going to replace all of these x's over here with u's, that includes this du dx. So what we're going to do is multiply both sides by dx and move that dx over here with all of the rest of the x's. So du equals 3x squared dx. So when we look over in our problem, 3x squared dx is right here. So now I'm going to take everything that I have and replace it with u values. So this would be the integral of, this part was u, x to the third plus u to the ninth, and then 3x squared dx is du. So I have the integral of u to the ninth du. And then we could just integrate as usual. So we're going to add 1, so we get u to the 10th over 10 plus c. So I'm going to replace u back with what it originally started as, and we're going to have 1/10, and then our u value is x cubed plus 5 to the 10th power plus c. So in this way, we can take the integral of functions that were composite functions to start out with, because this is what it was to begin with. So we don't have to multiply this out 10 times in order to undo it. We can just undo it using U-substitution. All right, for our second example here, they've chosen U to be the inside function of our trig function, where the angle is. So they let U equal x squared. So the derivative of U with respect to x is going to be 2x. We're going to multiply both sides by the dx. So du equals 2x dx. All right, so if we look over here, we have 2x dx right there. So when I rewrite this with U substitution, I'm going to have the cosine of U, and then du is the 2x dx, so du. Then I just integrate cosine. The integral of cosine is sine of U plus c. So then I just replace U. U is x squared, so sine of x squared plus c. All right, in our next problem, remember that this is sine of x to the fourth power cosine of x. So the inside function here is the sine x. That's why they chose that for U. U is sine x, so du dx is going to be cosine x, multiplied by the dx, so du equals cosine x dx. And so we have our cosine x dx right here. So we're ready to do our U substitution. We have U to the fourth power du. So we integrate that, and we get U to the fifth power over 5 plus c, or 1/5, and then replace U with sine of x to the fifth plus c. All right, in example 4, they've chosen for U to be the 2x, the inside of our trig function. So when we take the derivative, we get du dx equals 2. So if I multiply by the dx and move it to the other side, I get du equals 2 dx. But if we look at the problem, we've got a 1/2 dx, but we don't have a 2 dx, so this one doesn't match up. So we're going to do some manipulation here to make it match. The first thing I'm going to do is move this 1/2 out to the front. So I have 1/2 cosine of 2x dx. So I already know that I can replace this 2x with U. I need to replace dx with its equivalent. So if I were to divide both sides by 2 here, I should have erased that, then I get dx equals du over 2. So I'm going to replace this with du over 2. So I have 1/2 integral of cosine of U du over 2. Well, that's 1/2 du, so I could bring that 1/2 out to the front and just get 1/4 the integral of cosine of U du. And the integral of cosine is sine, so we have 1/4 sine of U plus c, or 1/4 sine of 2x plus c. So we have to do a little manipulation. If it doesn't fit exactly, we've got to figure out a way to make it fit. So I just moved the constant to the front since it didn't match what we needed. And then just solve for dx because I needed to replace dx. So I replaced it with du over 2, or 1/2 du. And then you can move that 1/2 out to the front as well. So if it doesn't quite match, you can do a little bit of manipulating to make it match. All right, in example 5, they let U equal 2x plus 1, which is the inside of this. Remember, this is x times 2x plus 1 to the 1/2 power. So that is my inside function. So the derivative of U with respect to x would be 2 again, multiplied by the dx. So du equals 2 dx. 2 dx. And again, that doesn't exactly match up. So we're going to have to do some manipulating again, but it's not like the one above where it was a constant that we could pull out. We can pull a constant out, but we can't take a variable and just pull it out to the front. So we're going to have to figure out how to replace x in this problem. So we're going to use this right here to replace x, because we already have a relationship between u and x. So now what we're going to do is solve this relationship for x. So we're going to have u minus 1 equals 2x, divide by 2. So x equals u minus 1 over 2. So it's going to look a little ugly at first, but then we can fix it up. So what we're going to have is the integral of, and then where the x is, we're going to put u minus 1 over 2. That replaces x, times, and then this 2x plus 1, which is u to the 1/2 power. And our dx has to be replaced, and our dx is equivalent to du over 2. So every single piece of this gets replaced with something with respect to u. All right, so in here I've got a 1/2 here and a 1/2 out here. I could bring that 1/4 to the front because those are constants. And then I have u minus 1 times u to the 1/2 du. And then I can distribute. So I have 1/4 the integral of u to the 3/2 minus u to the 1/2 du. And then I can just integrate as normal. So this would be 1/4 u to the 5/2 over 5/2 or times 2/5 minus u to the 3/2 over 3/2 or times 2/3 plus c. So I get 1/4 times 2/5, and u was 2x plus 1, so 2x plus 1 to the 5/2 minus 2/3 times 2x plus 1 to the 3/2 plus c. And then if we distribute the 1/4 in there, this would be 2/20 or 1/10, 2x plus 1 to the 5/2 minus, and this would be 2/12 or 1/6, 2x plus 1 to the 3/2. So, two things in these examples. In example 4, it didn't match up, but we had some constants that we could pull out and then kind of make it match. But remember, in example 5, we had an extra variable. Extra variables, you can't pull those out like you can a constant. You're going to have to replace them with a form of u, and so to do that, you're just going to take the equation you created and rearrange it so that you solve for x. All right, in example 6, they have asked us to let u equal the square root of x squared minus 1, but I'm going to change that so that we're still doing the same thing every time. So in every other problem, we've always let u equal the inside function, just the x squared minus 1. So that's what I'm going to do here as well. So just take that part off. We can do it this way, and I will do it that way with you later. But for today, I'd like to just keep it the same. So we're using the same process over and over again. So we're going to let u equal just the inside function, x squared minus 1. So du equals 2x dx. Du over dx equals 2x. Multiply, we get 2x dx. So when we look over here, we have an x to the 5th dx, but not a 2x dx. So I'm going to try to match a few things up with what I can. This dx, if I were to divide this by 2, then I would have an x dx. Well, here's an x dx. That would leave me with x times x to the 4th times the square root. So this thing right here, I'm going to use one of these x's and take this down to an x to the 4th. And this dx I'm going to replace with du over 2. So now I've still got an x to the 4th left. So what am I going to do with this? What I'm going to replace it with? So I'm going to manipulate my formula. This would be u plus 1 equals x squared. But I don't need x squared, I need x to the 4th. So I'm going to square both sides. So I get x to the 4th equals u plus 1 squared. So now I have a way to replace everything in the problem. So here we go. Replacing everything in the problem. This x to the 4th is going to be u plus 1 squared. This square root of x squared minus 1, or x squared minus 1 to the 1/2, would be u to the 1/2 power. This x dx is this single x dx, which is going to be replaced with du over 2. So we've taken care of everything in there. X to the 5th, we just split it up so that this x dx could be replaced here. The x to the 4th we replaced here. And this x squared minus 1 to the 1/2 power here. Alright, so now we've got it all replaced. That's the hard part. So we're ready to integrate like we always do. So we're going to bring the 1/2 out to the front times the integral. I need to multiply this out. So this is going to be u squared plus 2u plus 1 times u to the 1/2 du. Alright, so now I'm going to distribute the u to the 1/2. So u squared times u to the 1/2. When you multiply, you add the exponent. So that's going to be 2.5 or 5/2 plus 2u to the 1st times u to the 1/2 would be u to the 1.5 or 3/2 plus u to the 1/2 du. Okay, so now we're ready to integrate. So when I integrate, I add. So I'm going to get 1/2 and then u to the 7/2 over 7/2 or times 2/7 plus u to the 5/2 over 5/2 or times 2/5. But 2/5 times 2 would be 4/5 plus u to the 3/2 over 3/2 or times 2/3 plus c. So I have 1/2 times 2/7, and then u was x squared minus 1 to the 7/2 power plus 4/5 times x squared minus 1 to the 5/2 power plus 2/3 times x squared minus 1 to the 3/2 power plus c. Now all that's left is distributing my 1/2, so this would just end up being 2 over 14 or 1/7 x squared minus 1 to the 7/2 plus 4/5. That would be 2/5. 4 over 10 or 2/5 x squared minus 1 to the 5/2, and then 2/6 or 1/3 x squared minus 1 to the 3/2 power plus c. Alright, so our process is going to keep the same. We're always going to let u equal the function inside. Sometimes it's going to turn out that that's the denominator. We'll talk about that as well. And if you'll do that and let that be your u value, then u substitution should work for you for your composite function.